This is Team 3. I'm Cameron Ford.
I'm Xander Dressler.
I'm Lorenzo Patton.
I'm Tice Colin, and we're doing a presentation over Northwestern Grant Intersection Design, the Saukers. Many pedestrians tend to jaywalk when they are crossing the street instead of waiting for the allotted time in which they can cross, making the intersection unsafe. The solution is important to creating a safer environment for students when crossing the streets. We must consider an economical and environmentally friendly design for the users and the stakeholders to implement. Our users for this project include drivers, pedestrians, and Purdue students, and then our clients and stakeholders include the University of Purdue, as well as the Department of Transportation. Having biodegradable materials and being environmental friendly, along with weather resistant and considering weather patterns in West Lafayette, Indiana. Another criteria for our problem is making sure it's scenic pleasure. To go along with this, our constraints are our product must be affordable and must provide safety for the consumers. In searching for solutions, we first roughly sketched out different ideas, and then we also used a low fidelity prototype in class to expand on those ideas that were sketched. Following this, we used functional decomposition to break our problem down into smaller and smaller problems in order to provide solutions for each problem. Finally, we used prior art in order to base our ideas off of things that have already been tested.
Our first alternative solution was a crosswalk with lights and sensors. Once a pedestrian crosses the road, the sensors pick it up, and which makes the crosswalk illuminate red, signaling the driver that pedestrians are crossing to make it safer for both the pedestrian and driver.
For our second alternative, we decided to go with speed bumps.
In this Minecraft model, it shows a sign that alerts the driver of an incoming speed bump 500 feet or 166 blocks away. And once the driver approaches the speed bump, it significantly decelerates their speed in order to help the pedestrian to safely cross.
For our alternative solution number 3, it was a crosswalk sign with LEDs and alarm. Right here you can see reflective material showing the crosswalk better to drivers. And then up here you can see the black and white area is where the speakers providing alarm for the drivers.
With that in mind, we have a special guest present our final solution.
Oh, hey guys, Peter Griffin here. How many times have you found yourself in a hurry, but the stupid traffic is in the way? Introducing Team 3's latest invention, the Smart X Walk. This ingenious design aims to better alert oncoming traffic of pedestrians crossing in intersections. After tripping a sensor, bright red LED lights along the crosswalk light up to help keep Purdue students safe and sound. Gee, this thing could have really saved me some trouble a few times back in the day coming home from the clam.
Our prototype was created using an Arduino board, some coding, wires, LED diodes, pack batteries, and an echolocation sensor.
The final solution holds both criteria and constraints, the most important one being safety for both pedestrians and drivers when crossing or driving through the road at the intersection, along with having good weather-resistant properties to withhold good strong weather for Purdue, such as when it snows, rains, and whatnot.
It also excels at keeping a pleasant scenic environment.
With lights and sensors goes as follows. The lights cost $3,600 and the 10 sensors needed cost $500 each, with an installation fee of $1,500, coming out to a total of $10,100. The installation is also efficient, since system installation only takes 2 days, with light syncing and testing only taking 1 day, for a total of 3 days of installation.
When weighing how important each criteria and constraint are, we decided that cost and versatility were the two most important things.
Using those weighted metrics, we decided that Design 1 was overall the best design, given that it has 205 points compared to 145 and 150 on the other designs.
In terms of trade-offs and limitations, the first limitation that we had for this product is that there was a maintenance and installation issue where we were not able to actually install this into a real-life setting, and maintenance would be very difficult as compared to our alternative systems. The second issue that we came across when it came to limitations is limited testing on a new product, as we're not able to actually install this because of permissions by the school and local government, and we also were not able to get feedback. Therefore, we do not have much credibility on this product. Our last one was the modifications, as they are very difficult and expensive.